Okay. Okay, so we wrap up discussions on non-relativistic case and then move on to Lorentz invariant theories later today. So let me wrap up the subject, which is actually related to the current homework problem, which is an idea called resonance. So we talked about this scattering. You send in a photon on atom, and a photon gets scattered off an atom in a different direction. And that's a scattering process we talked about. We figured out how to compute what is called the cross-section. That's the rate of the scattering process per flux of the photon you put in. And we looked at the dimensionality of these quantities, so just verify that it indeed has the dimension of the cross-section, namely area. And so we also derived accordingly the formula for the cross-section at the second order perturbation theory. And so that's what we actually used to compute the radius scattering cross-section, and then figured out why the sky is blue and sun is orange. So that was actually a very important phenomenon, which we of course see every day. Now I can pose a different question here though. So in the case of radius scattering, we talked about a photon whose energy was much smaller compared to the atomic excitation energy. So suppose this is the hydrogen atom, and if all the atoms are in the ground state of oneness, then the lowest atomic excitation energy is the energy splitting between the 2p and oneness state, which can be caused by this dipole transition we talked about, and we even worked out the selection rule for that. So when the energy of the photon you send in is less, much less than the excitation energy from oneness to 2p, that's the case that corresponds to radius scattering. And what's going on here, Tom? Something wrong?
No, I think it's okay. Sorry about that. Nothing
Okay.
happens.
Oh, nothing happens? Okay, good. I just wanted to make sure. So I saw you moving back and forth, so I was wondering something was wrong with it. Okay, never mind. So the energy difference between 1s and 2p state would correspond to a photon in the ultraviolet. And ultraviolet, of course, photon has a much shorter wavelength than, for example, red light, which has a much longer wavelength. And longer wavelength corresponds to lower energy photon. So that was the limit we talked about. But just imagine that you send in a photon whose energy is just exactly the energy difference between 1s and 2p state. Then you know what should happen in that case, right? Because you send in a photon on the 1s state of the hydrogen atom. And if the energy of the photon is precisely the energy difference between 1s and 2p, you would expect that the hydrogen atom get excited to the 2p state. And in this formula for the second order perturbation theory, I emphasize the fact that this intermediate state M doesn't satisfy energy conservation. And therefore, this state has to be virtual, namely that you do not observe the state being excited to the intermediate state M, or like 2p state in this case, because it doesn't satisfy the energy conservation. But if it happens that energy of the photon you send in is precisely the energy difference between 1s and 2p state, you do expect the atom get excited to 2p state. So that's the state you expect. You can observe the hydrogen atom to get excited to the 2p state for real. Then you're not talking about a virtual situation. You're talking about a real situation of atomic excitation by absorbing a photon. But then you realize that there's something wrong with this formula. So if the energy of the initial state, that is the energy of the oneness state plus the energy of the photon, and energy of the 2p state in the denominator are exactly the same, you find EI minus EM to vanish, then this quantity seems to become infinite. So something is wrong with that idea. So what happens when you send in exactly the right energy of the photon to excite the atom from oneness to 2p state? And that's the question we have to answer. So in that case, the one little thing you, I'm sure, have noticed already is this little I epsilon. And we introduced this little I epsilon for the purpose of forcing the time integral to converge when you use the time-dependent perturbation theory from infinite past to the infinite future. So we introduced this I epsilon as a mathematical trick. But it seems that there's something actually important about this when EI and EM are the same, so that denominator vanishes, except for this I epsilon piece. So we have to think back at what is going on with the I epsilon piece. So that's the question. And here is the answer, and I will justify this answer in a moment. So it turns out that when the energy of the photon you send in is exactly the same as this excitation energy from 1s to 2p, then certainly you do expect that the atom to get excited from 1s state to 2p state for real, because that does satisfy the energy conservation. And the answer to avoid this infinite cross-section turns out to be that you need to introduce actually the imaginary part to the energy of the 2p state. And that's what this homework problem is actually about. So the idea is that the energy of the 2p state is no longer real, becomes slightly complex. And the reason why the energy becomes slightly complex is that 2p state, as we have computed already last week, is actually no longer a stable state. It actually decays. And when a state decays, then your energy dependence or time dependence of the state is no longer just e to the minus IET over h bar, but you have this decaying behavior, which is e to the minus t over 2 tau. So that the state squared probability would go down like e to the t minus tau, where tau is the lifetime of that state. So that actually corresponds to the energy eigenvalue being complex. The imaginary part would correspond to the lifetime of the state. So what I would like to show you in the next few slides, which is of course the same thing as a homework problem, so I'm sort of giving it away, is the idea that how you actually get this imaginary part in the denominator, which is basically the idea that energy of the 2p state now receives a perturbation from the interaction to the photon to acquire the imaginary part. So that's the idea I'd like to explain on the next few slides. But anyway, so before going to the explanation, any questions about this idea?
What exactly is the difference between the I epsilon from before and this I gamma? I mean, they're both imaginary, right?
Mm-hmm. Yeah, so that will come up on the next slide. So please wait for that. Thank you. Any other questions here? Okay, so of course, once the energy does acquire this imaginary part, even when EI and EM are the same, so that the real part vanishes, the imaginary part remains, so the cross-section does remain finite. And so that's the way everything turns out to be consistent. So the rest of the discussion is to understand how this imaginary part is acquired by the energy of the 2p state. So here's the deal. So when you actually compute the energy shift from perturbation theory, and then you find this expression. And this is the expression you probably have seen in a time-independent perturbation theory in quantum mechanics class. And when you go through the time-dependent perturbation theory, it acquires this I epsilon piece. And then one way to understand it is just looking back at the time evolution operator in the time-dependent perturbation theory, and expand that in power series in time t, and then identify the coefficient of t as the energy of the state, right? Because e to the minus IET over h bar expanded in power series in t has the coefficient minus IE over h bar of the linear order in t. So if you do that, you find the energy shift, which has this additional piece. And it's consistent with time-independent perturbation theory, except for this additional factor of I epsilon. So if you take this formula for the energy shift from perturbation theory, and then remember what you actually study in the complex analysis, 1 over x plus I epsilon as an analytic function of x can be understood, if this is inside an integral, as a sum of 2 pieces. One of them is called the principal value integral, and another piece is the imaginary part, is a delta function. So in the case of the complex analysis, you do the contour integral. So whenever you actually integrate a function, you specify a path on a complex plane. So suppose this is the real axis. So x goes from negative infinity to positive infinity. And naively, if you have 1 over x, of course, you have a singularity where x is 0 at the origin. Now that we have this I epsilon piece, what it does is to force this integration contour to go above the singularity. So if you take the epsilon to be finite, the pole where the integrand becomes singular is where x is negative I epsilon. That's where the denominator vanishes. So negative I epsilon is below the real axis. So that's the same thing as doing the integral along the real axis where the pole is below the real axis. If you just analytically continue it, then it's the same thing as going over the pole, not under the pole. So the definite sign here, plus the plus sign in the denominator, gives you a prescription that you're supposed to avoid the pole above it, not below it. And one thing you also know from the contour integral is that if you go around the pole full circle, you get minus 2 pi I times the residue. The residue is the value of the numerator at the singularity. So if you go above the pole, that's a half the circle. So instead of getting minus 2 pi I for the value at the pole, you get minus pi I. And that's this piece here. So you get a piece by going around this pole, above the pole. You get a contribution which is negative I pi times the value of the numerator evaluated at x equals 0. So that's what this delta function is supposed to give you. And the rest of the integral, now removing this half circle, is an integral from negative infinity up to close to the pole, and also the piece that starts just above the pole all the way going to infinity. And the prescription is that you need to keep the same distance away from the pole, both into the negative side and positive side, and then try to take the limit where this interval shrinks to 0. And you can see why that is regular, because 1 over x is an odd function. So the piece just below the pole and piece just above the pole actually cancel against each other. So by taking the prescription that you actually take the limit symmetrically from above and below, then you avoid the singularity so that this limit is actually a convergence. So this is the idea of dealing with this I epsilon in the complex analysis. And if you're not familiar with this idea, then I urge you to consult the miscellaneous note I actually posted on B courses contour.pdf, which talks a lot about how to actually use this idea of sort of the Cauchy's theorem, that in Cauchy's theorem tells you that you can freely deform your contour on complex integrals as long as it doesn't hit the singularity. And Cauchy's theorem then also tells you that when you actually go around the pole, that gives you precisely negative 2 pi I mentioned just a minute ago. And using the same ideas of you can freely deform the contour together with this idea that the contribution around the pole gives you this minus 2 pi I, justifies this idea that you can divide up this original integral with I epsilon downstairs into the real part which is this principal value integral, you take the symmetrical limit of approaching the singularity, and the imaginary part, that is a delta function. And in that miscellaneous notes, you also see a bunch of examples where you can actually use this idea of the complex integral to actually obtain the rather non-trivial integrals done using the technique. So what I'm going to use here is just take this identity for granted and ask the question, what is the contribution to the energy shift from the perturbation theory, and in particular its imaginary part? So by looking at the imaginary part of this expression, the numerator is manifestly real. So this is the matrix element of initial state I going to the intermediate state capital I, and the other matrix element from capital I to I. So the second matrix element is the complex conjugate of the first matrix element, because V is a Hermitian operator. That's a part of the Hamiltonian, obviously. So the numerator is manifestly real. So the only thing that can be imaginary in this expression is coming from this I epsilon, and therefore this piece of the delta function. So looking at the imaginary part of how the energy of the 2p state would change by the second order perturbation theory, then is given by this expression over here. So this denominator is what corresponds to this identity. So X then is EI minus E capital I. And so using this identity, imaginary part is negative I pi, that's over here, times the delta function of X, that's the delta of EI minus E capital I. And the rest is the numerator in this original expression for the energy shift. So that's the imaginary part the 2p state actually acquires in its energy. And then if you remember the Fermi's golden rule, then this expression is precisely the decay rate of the 2p state. So that's the probability per unit time, how much 2p state would go into this initial state I. In our case, that's the initial state with ground state 1s and the photon. So that's the decay rate of the 2p state going to the photon and 1s ground state. So this imaginary part of the energy of the 2p state precisely corresponds to the decay rate. And we write h bar times decay rate as gamma for the sake of discussion later. And so what you see then is the energy of the 2p state now has a complex energy. So initial energy of the 2p state you compute in the hydrogen atom in quantum mechanics classes over here. And then comes the energy shift, which is this imaginary part we just computed, which is related to the decay rate of the 2p state up to a factor of h bar. So the idea is that this is the phenomenon called the resonance. So first of all, once the energy is complex, just the usual behavior of the solution to the Schrödinger equation is that you get this phase of the wave function that goes like e to the minus I energy times t of h bar, right? So that's the solution to the Schrödinger equation for the stationary solutions. But now that the energy is complex, I have to also put in this imaginary part to this time dependence of the stationary state. And this imaginary part, together with the minus I up front, now gives you a real exponent, which is exponentially decaying as a function of time. So if you take the absolute square to compute the probability, so even though we are looking at the energy eigenstate, it's no longer stationary, it actually damps exponentially as a function of time. And this gamma, which appears as the imaginary part of the energy over h bar, is the decay rate W. And we talked about this. The W decay rate is the inverse of the lifetime, average lifetime of the state. So again, quantum mechanics doesn't give you prediction on when exactly a particular atom would decay. Each atom would decay on its own time scale, but on average, you find a characteristic lifetime. and that's this tau over here. So this imaginary part of the energy is what gives you this exponential decay law. So you find this relationship that the lifetime tau is the inverse of this gamma, imaginary part of energy, up to a factor of h bar. So this is how you obtain the imaginary part of the energy from the second order perturbation theory. And once you find that the 2p state has now a complex energy, when you go back and use this second order perturbation theory, this m, that's the intermediate state in this case, has now a complex energy. So in addition to the real part of the energy of the 2p state you compute in a hydrogen atom, now you also need to stick in the imaginary part as well. And now that imaginary part is finite, you can ignore I epsilon that was meant to be infinitesimal. So I drop I epsilon instead and keep this I gamma over 2 in the denominator. So by doing so, the cross-section now has become finite. So the answering question to Sahil, that there used to be I epsilon, now I'm changing it to I gamma over 2, and that's simply because EM now has the imaginary part, that's minus I gamma over 2. And once you stick in the imaginary part of EM, then I can safely drop I epsilon because there's no infinite cross-section anymore. Everything is regular, so dropping I epsilon is totally justified. So I epsilon indeed was a mathematical trick to regulate, namely to make the integral finite, but that regulator I don't need anymore once I know that energy has this imaginary part, it's a complex energy instead, and the cross-section remains finite even when you hit exactly the right energy to excite the atom. So that's the idea of what's going on here, namely that at second order perturbation theory, the state, which is unstable, acquires the imaginary part due to Fermi's golden rule. And once the state acquires the imaginary part in its energy, that is the sign that the state actually decays. And that makes sense because that's what you learn from Fermi's golden rule, namely that you have this decay rate because the state does decay. And when the state does decay, then the probability to be in that state damps exponentially as a function of time with a characteristic lifetime. And we computed already that lifetime has to do with this rate, inverse of the rate. And so the idea is that the energy of the state now acquires an imaginary part, which corresponds to the h bar over lifetime. And just to make sure that this makes sense, the time times h bar has the dimension of energy. So the gamma indeed has a dimension of energy. So that's why it qualifies to come together with EI here. And hence, this is the imaginary part of the energy. So the gamma is called the width of the state, namely that this is how much energy can actually move away from the nominal energy of the 2p state. And that's what I'm going to show you on the next slide. But anyway, let me stop here. So this is the idea how the energy of an unstable state acquires an imaginary part to its energy because that's consistent with this exponential decay of the state that is unstable. Okay, any questions about this?
How exactly, so I understand that we got the delta E as this, imaginary part with the rate, but I guess I just didn't understand the next bullet point about how we go from that to the energy now having this imaginary part. I guess there's a logical step.
Right. So that's just because this is the formula on how much energy would shift by perturbation of the system. And this perturbation, the energy shift, has a real part, but now it also has the imaginary part. So this energy shift in perturbation theory is meant to be added to the zeroth order energy. That's the energy of the 2p state you compute with this Lagrange polynomial in hydrogen atom in quantum mechanics class. So original E2p you compute from hydrogen atom plus this delta E, is now the energy of the 2p state, including perturbation of the system. So that's the idea of perturbation theory, right? So this is supposed to be added to the original energy of the 2p state before you put in perturbation. But it just happens that this energy shift has the imaginary part as well. So imaginary part also needs to be added to the original unperturbed energy of the 2p state. And we regard the whole thing as now the new energy of the 2p state, which includes the perturbation to the system. So that's why this whole thing now has the interpretation being the energy of the 2p state, now including the perturbation of the system. And this energy is now going into the solution of Schrödinger equation of this phase e to the minus IE t over h bar. But even though this used to be a phase when 2p energy was just pure real, but now that it has the imaginary part, it's no longer just pure phase, but it has a real part to it, which corresponds to this exponential decay. Does that answer your question?
I see. So the energy shift appears in, I guess like before we were seeing it in calculating the rate of transition, right, through degenerate perturbation theory, but this term in particular also gives us the energy shift as well, right?
Right.
By itself.
That's right.
Okay.
Any other questions here?
I've got a quick question.
Go ahead.
Is the equation like I over x plus I epsilon, is this equation valid all the time, or is this valid upon integration?
Oh, so this identity is meant to be inside an integral.
Okay, so if that is only valid inside the integral, how can you like write like imaginary part of delta EI? Because delta EI is not, we don't integrate delta EI, right?
So if you remember what we did when we computed the lifetime of 2p state, we had to sum over all the final states. And sum of the final states is actually a phase space integral over the momentum of the photon. And the momentum of the photon is now written in the spherical coordinate on the radial piece in the solid angle. And radial piece is an integral over the energy of the photon. So that's how this delta function can be integrated. So this sum over the states is actually an integral. That's why I'm allowed to use this identity to rewrite this denominator with I epsilon in favor of the delta function. And in the end, you really do integrate over the final state of photons, so the delta function in the end disappears. Everything is regular.
Okay,
is that okay?
Yeah.
Okay.
Yeah,
good.
I see.
Thanks for asking that question too. Any other questions here? Okay. So this idea is probably a bit mind-boggling, because we get told in quantum mechanics class is that energy is an eigenvalue of Hamiltonian, and because Hamiltonian is a Hermitian operator, eigenvalue has to be real. What's going on here is that even though Hamiltonian is real, the eigenvalue is now complex. And the reason being that you're looking at a situation where the photon is moving away from the atom as the 2p state decays, and photon moving away from the atom is not normalizable state. And if the state is not normalizable, usual proof you do to show why the eigenvalue of a Hermitian operator is real doesn't apply anymore, because you cannot ignore the surface term. So it turns out that this idea that the energy is actually complex is not inconsistent. And if you want to know more about this idea that the Hermitian operator can give you a complex eigenvalue, I highly recommend you to read the textbook by Landau and Lifshitz on quantum mechanics, where they detail the idea that energy is actually allowed to be complex. And hence that corresponds to this exponentially decaying unstable state. So what I would like to show you next is what it actually means in practice for the cross-section, which was the puzzle we started out with. So we were worried that cross-section might become infinite when you hit exactly the right energy to excite an atom. But now that this I epsilon is replaced by I gamma, the cross-section does not become infinite, stays finite, but nonetheless, it can become very large because the gamma is second-order perturbation theory, namely that it is supposed to be small compared to the energy of the 2p state to begin with. So even though the cross-section is now guaranteed to be finite, it can be large. So that's the expression we see over here. So now that we put in this width gamma, which is the h bar over the lifetime of the 2p state, into this formula for the cross-section. And when you send in a photon that is pretty close to the excitation energy to excite the atom from 1s state to 2p state, that's the situation we are looking at, then this denominator nearly vanishes except for this complex imaginary part. So if you view this cross-section as a function of the energy of the photon you send in, the second term becomes large, so I can ignore the first term and just focus on the second term and look at the behavior coming from this nearly vanishing denominator. So that's this expression over here. I just extracted the behavior coming from this denominator. And this is absolute square of this complex denominator. So I can just easily work out this is the real part squared plus imaginary part squared, right? And as a function of energy of the photon, that's EI, then it has this peak. It no longer diverges. It's finite, but nonetheless, it has this big peak. And if the energy is hitting exactly the excitation energy, then this peak is very high because it's 1 over gamma squared, where gamma is small because that's a quantity appearing in second-order perturbation theory. So this is the high peak. When the energy of the photon starts to move away from the excitation energy, it starts to go down, but it's not that it immediately goes down to 0. So there is actually a finite range of energies where you have this peak. And you speak of FWHM, full width half maximum. And that's the idea that when you look at the height at the half of the peak. So if I normalize this peak to be 1, then half height is 0.5, that's over here. And full width is the range of the energies where you hit this half the peak. And that's the idea of full width half maximum. And so this gamma over here corresponds to full width half maximum of this function over energy. And this function, which is 1 over energy difference squared plus gamma squared over 4, is called the Lorentzian distribution, or is also called the Bright-Wigner distribution. And Lorentzian or Bright-Wigner is the characteristic shape of the energy dependence of the cross-section when you hit the energy exactly right to excite the system to an unstable excited state. But you don't need to hit the energy exactly to get a large cross-section because the 2p state now has a finite width. In some sense, energy of the 2p state is now a little blurred because of this imaginary part. 2p state no longer has a sharp energy. You don't need to hit it exactly right, but even if you hit it just slightly off, you still get a large cross-section. So that's what I meant, that energy of the 2p state is a little bit blurred. And so this is actually a manifestation of an energy time uncertain principle, namely that energy of the 2p state is now a little blurred. So there's a delta E. This the energy of the 2p state now has a delta. There's a little uncertainty in the energy of the 2p state. And energy of the 2p state is uncertain by an amount given by the width. And width is h bar over lifetime. The lifetime is how long 2p state can exist. That's delta t. So what you're supposed to do in the last part of the homework problem is to just to reproduce what I just said in words, namely that width of this energy in a 2p state corresponds to actually inverse of delta t, which is the 1/lifetime of the 2p state. Hence, that's the energy time uncertainty principle. So anyway, so the main message on this slide is that good, cross-section is now finite, which is great because we don't want infinite result in physics. Every physical quantity should be finite. But this finite cross-section now has a big peak when you send in the photon at the right energy to excite the system to 2p state. But it doesn't have to be exactly the right energy because a 2p state now has a little blurry energy. There's a uncertainty energy of the 2p, which is given by the width. And the width, which is uncertainty in energy, is given by h bar over lifetime of the 2p state. And the lifetime is delta t, and hence this is one example of energy time uncertainty principle. Okay, so let me stop here again and see if there are any questions. No? Okay, I'm pretty sure this is actually rather confusing subject conceptually, and that's why I'm pausing here for questions. Are you sure it's okay? All right. And I think the very last part of the homework problem is to actually go back to the time domain. So this behavior you are looking at right now is a function of the energy of the photon you are sending in. So this is in some sense the frequency domain because energy is the h bar times angular frequency, right? So this is the behavior in the frequency domain if I use the language in the Fourier analysis. And I can go back to the time domain. So the idea between the frequency domain and time domain is the Fourier transform. So if you have this behavior in the amplitude with this complex denominator, and I can do the Fourier transform of that behavior and go to the time domain as a function of t now. So this expression in the cross-section was a function of energy. Now I'm going to a function of time t by doing the Fourier transform. So the idea is that I put this exponential oscillating frequency factor as a function of energy of the photon you're sending in, and you integrate over the energy. And this integral is again another example of this Cauchy integral. So energy of the photon you're sending in is of course real. So that's an integral over the real along the real axis. But when t is positive, I can add additional section coming back in half circle on the complex plane because in the limit of infinite e, so I extend this contour all the way to the infinity, then this numerator damps exponentially. So this half circle adds only 0 to the final result. If the t is negative, then you can't do this because the sign of the exponent becomes positive on the lower half plane. So this is not 0, it's exponentially large instead. So what you are allowed to do instead is to go back on the upper complex plane. Then you find a piece which is exponentially damping, so you're adding 0 to it without changing the result. So depending on whether t is positive, in that case you come back on the lower half plane, or when t is negative, you come back on the upper half plane. But now that idea of this integral over the complex plane allows you to deform the contour of the integral as long as you don't see the singularity. This integral coming back on lower half plane, I can just shrink this contour to a little circle around the pole. And what we just talked about on the previous slides is that integral around the pole gives you minus 2 pi r. So if you come back on the lower half circle, then the integral reduces to a circle around the pole, and location of the pole where this denominator vanishes is where EI is EM minus I gamma over 2. So that's this location of the pole. So I go around this circle. That gives me negative 2 pi I. And the residue, namely the delta function piece, corresponds to, just by substituting EI, that's the integration variable, by the location of the pole, EM minus half I gamma M. So I substitute this combination into EI in the numerator, and that gives me this exponential expression. And that expression is precisely the exponentially damping behavior of the decaying unstable state. So this is the way we come back in full circle. So I told you the idea that something decaying should correspond to the complex energy. We indeed did work out the complex energy from second order perturbation theory. And that complex energy gives you this finite cross-section as a function of energy with this Lorentzian or Bright-Wigner distribution. And that behavior as a function of energy now allows you to go back to time domain where you can indeed identify this exponentially decaying behavior. So this is how everything turns out to be consistent. On the other hand, when time is negative, then I can't go back on the lower half plane. I have to come back on the upper half plane. And there's no pole in the upper half plane. So I can keep shrinking this integration contour all the way to 0, and integral vanishes. So this is the behavior that's a step function. So you have exactly 0 when time is negative. And that is basically that you haven't excited the atom yet. So you were just about to send in the photon, and before time 0, you haven't excited the atom yet. And at time 0, you excite the atom from 1s state to 2p state. But after you excite the atom to 2p state, it starts to decay exponentially. So that's the behavior you were seeing from this integral now in time domain. It's exactly 0 up to the point you excite the atom. Then you boom, you have now probability 1. Then from that point on, the 2p state would only decay exponentially. And that's the behavior you identify just by going back to the time domain of this complex amplitude of the scattering. And as I said, this is the manifestation of the energy time uncertainty principle. Okay, any questions about this?
Why exactly are we allowed to shrink the integral if it's supposed to range from negative infinity to positive infinity?
So that's the Cauchy's theorem. And I wanted to ask you this question. So how many of you have not seen discussions on the Cauchy's theorem and the contour integral? So this is what is called the contour integral. You integrate along a path on a complex plane where you are freely allowed to deform the contour as long as you don't hit the singularity. There's nothing embarrassing about this. So if you haven't seen this before, just raise your hand, please. Well, you have all seen this? Okay, that's actually great. So the idea what I'm using here is that initial integral was all the way from negative infinity to positive infinity along the real axis. But when time is positive, I'm allowed to add an infinite half circle on the lower half plane because that is 0. It's exponentially 0. So now I have a closed contour. Rather than just an integral along the real axis, which is an open integral, there are no ends to it. Now I added this half circle at infinity. So the integral actually comes back, giving you a closed contour. And when you have a closed contour, then you have a contour integral. And contour integral can be deformed freely, according to Cauchy's theorem, for an analytic function in the integrand. So you have this infinite line integral and half circle integral, which is a closed contour. But as long as I don't hit the singularity, I'm allowed to change the contour continuously and keep deforming it to a smaller and smaller contour, closed contour. eventually to the point that I'm no longer allowed to change the contour because I hit the singularity. So I can shrink this infinite contour all the way to an infinitesimal circle around this pole. And that's the contribution I just computed over here. So does that answer your question, Sahil?
Yeah. So I mean, I've seen this before in 137b, but I guess we just didn't go into deforming the contour once it's
I see.
been formed.
Okay.
Yeah.
So I do encourage to look at this miscellaneous notes on the contour integral to get sort of more intuition on how you can do this and how actually useful, incredibly useful that is in evaluating rather almost formidable, impossible looking integral, which can be done actually using this trick of the contour integral.
Yeah, I guess the rule that I remember is that if you enclose the singularity, like regardless whatever the shape of the contour is, you just get the 2 pi I and the function evaluated at that singularity, right?
That's right. That's what I'm doing indeed. And 2 pi I corresponds to anti-clockwise contour. Here I have a clockwise contour. That's why it's negative 2 pi I instead of 2 pi I. But apart from that, it's the same idea. Okay. Thanks for asking the question. Any other questions here? So I hope. Go ahead, Ryan.
Sorry. Okay. So all the thing that you talked about here seems like simultaneously at t equals 0. So if the source that can emit photon is very far away from the atom, does that like violate the special relativity, something like that?
Well, with the photon eventually come to the atom, right? You're sending the photon from infinity and eventually come to the atom, and that is time 0. So the origin of time is some arbitrary pick. So when I do the Fourier transform, going back to time domain, I was allowed to put, for example, arbitrary offset in time in the numerator. So I chose the simplest numerator for the purpose of doing this integral, which happens to correspond to the situation that I define the origin of time to be the moment when the atom gets excited. So the experiment starts with time at negative infinity. You are sending photon infinitely away from the atom, and photon starts to approach the atom, basically hit the atom at time 0, the atom gets excited to 2p state, and then it starts to decay exponentially. So that's the behavior. So it's 0 all the way up to time equals 0, then boom, the atom gets excited, and then starts to decay exponentially. And that's a behavior you can identify by going back to the time domain. Does that answer your question, Ryan?
Yes.
Okay.
Thanks.
So just to recap what we have done, so we had this puzzle that the cross-section seems to diverge when you hit exactly the right energy to excite the atom from 1s state to 2p state. But now we know it's not infinite, it's actually finite, because the energy of the 2p state has this imaginary part. And what we computed here is the energy shift of the 2p state at the second order in perturbation theory. And indeed, we could identify the imaginary part of how much energy shifts for the 2p state from the perturbation to the system. And so we had this idea that the imaginary part of the energy should correspond to exponential decay. Here, I immediately put in the eigenvalue into the exponent. So this was actually a sloppy argument. But now we made the argument more precise. Once you know that energy has a quiet imaginary part, what we know is the cross-section is now finite, as we wanted to understand from the beginning. And the cross-section is finite, but has a peak. And behavior near the peak can be given only by this behavior of the denominator. And this behavior of the denominator is a function of energy, namely that this is behavior in a frequency domain. But now this behavior as a function of energy or frequency of the photon can be brought back to time domain. Then you clearly do identify this exponential decay law. So this is now a precise argument. Rather than heuristically just putting in the imaginary part of the photon at the 2p state in the exponent, now I justified why putting it in is the correct thing to do to identify the time dependence of this state of the 2p. And because this behavior that you have a peak in cross-section is very similar to when you're actually bringing in a tuning fork to your guitar. And when the frequency of the sound of the tuning fork is the same as the frequency of the string on your guitar, then just by bringing the tuning fork close to the guitar, you don't touch the string at all, but the string starts to vibrate. And that is the idea called the resonance, right? So that's exactly the same phenomenon. So as a matter of fact, I have just a reminder over here on the solution in classical mechanics of a forced oscillator. So when you have this my double dot plus m omega naught squared y, that's the equation of motion for the harmonic oscillator. And this is a forced oscillator because I have now a source term, which also vibrates with the frequency omega. But this is a damped oscillator because I also have a force term, which depends on the velocity, which is the friction term. So this is a harmonic oscillator, which is driven by a force together with the friction. And you may have solved this equation in classical mechanics class. You'll find this solution. And now you see this behavior of the Lorentzian distribution. So this omega squared difference is exactly the same behavior as the energy difference squared. And then you have this piece that is coming from the friction, which is the B, the friction term. And this is a Lorentzian distribution in the frequency domain. So this is the idea of the resonance, namely when you hit the right frequency of the force you're applying, namely bringing a tuning fork with the right frequency, which corresponds to the frequency of the string on the guitar, then the string starts to vibrate with a large amplitude given by how much force you're applying, basically from the sound wave coming out from this tuning fork. And then you see a high peak as a function of the frequency, which is in this Lorentzian distribution. And what you see here as a function of the energy of the photon, as I said, is just h bar times the angular frequency. So it's the same idea. This is the behavior in the frequency domain, that amplitude of the forced oscillator, namely that sending in a photon forces oscillator, namely from 1s state to 2p state, is an oscillation to be created. And how much it creates is given by the inverse of the width, because the width basically corresponds to the friction. And friction is what makes your oscillation damp. And that's the same idea of this exponential decay of an unstable state. So this is in precise analogy to this forced damp oscillator you may have seen in a classical mechanics class, and what corresponds to the lifetime of the unstable state in the quantum physics is nothing but the friction that makes the oscillator damp exponentially, and indeed this exponential decay. So that's the idea. I hope that makes sense. Any questions about this whole thing?
Perhaps this is a nitpick, but what happened to the factor of 2 pi between taking the Fourier transform and evaluating the probability distribution from it?
Okay, thank you. So you're talking about this 2 pi, which I didn't write at the bottom of the slide, right? So that's the 2 pi. Yeah. So when you actually go from, when you do a Fourier transform, and you might remember going from X space to P space,
thank you.
That you have factor over square root 2 pi for each of them. And because I didn't write factor of square root 2 pi in neither T integral nor E integral, after doing an inverse Fourier transform, I end up getting factor of 2 pi. Okay?
Right, thank you.
Good, good. No, this is a good question. Any other questions here? So in some sense, now you understand what's going on with the absorption of the photon, right? So when you say the atom can absorb a photon to go to an excited state, and that's what you get told in quantum mechanics class, what is actually going on is this resonant scattering. Because when you're sending a photon to excite an atom, it doesn't stay in excited state forever. It decays. So it's actually not precisely correct to say that you absorb the photon. It's part of the entire scattering process. You are sending in a photon, 1s state gets excited to p state, but the 2p state now de-excites by emitting a photon. So the entire process is photon coming to an atom, and photon gets scattered by an atom. That is the whole process. So it's a little loose to say this is an absorption of photon. Of course, that's a very useful concept. That's why we talk about it. But that's what's actually going on. So both absorption of the photon and emission of the photon through an excited state is part of the scattering process. You can never have an initial state of the atom to be 2p because it doesn't stay there forever. You have to create 2p state by sending in a photon. So this is a scattering process. And also that it's not entirely correct to say that you can absorb a photon when energy of the photon is precisely that of the energy difference between the ground state and excitation state, because energy is a little bit blurred. The energy you send into the photon may deviate from precisely the excitation energy by an amount given by the width. So what you got told in quantum mechanics class was a little loose in 2 counts. Absorption and emission is not an independent process, it's part of the scattering process. And second, these emission lines you have, I'm sure, seen as an evidence for quantum mechanics is not a sharp line, they have width. Because the energy of photon, namely the excitation energy from 1s to 2p state, is a little bit blurred. And that's something you can actually verify experimentally. And in the case of 2p to 1s transition, it's sharp enough that it's very difficult to resolve the width of the energy of the photon. But there are other states which are much shorter lived. And you can really scan the scattering process by sending in photon of different energies. So you measure the cross-section as a function of energy, and you put the data points on how big the cross-section is as a function of energy. And you put a lot of dots on its way. And you can verify that it indeed has this Lorentzian, or what is called the Bright-Wigner distribution. And Lorentzian is the name was given for this classical harmonic oscillator. And when people discover that energy dependence of the cross-section also has the same form, and that is due to the people, Bright and Wigner. So that's why it's a Bright-Wigner distribution, especially in the context of quantum physics. So the energy of the photon that can be absorbed by the atom is not precisely the excitation energy, because that is a little bit blurred by the inverse lifetime of the excited state. And that's something you can actually measure experimentally. I probably should have looked up some experimental data for this purpose and show it to you. I didn't. Maybe if I find one quickly, I might actually put that into the slides when I repost the slides for the lecture today. Okay, so that finishes up my discussion on resonance. Any further questions on this point? After this, I actually now finally move into Lorentz invariant quantum field theory. It's okay? All right. So now we move into Lorentz invariant quantum field theory. So Lorentz invariance is something I'm sure you have also studied in some other classes. And we know Maxwell's theory of electromagnetism is Lorentz invariant. Indeed, Lorentz discovered Lorentz invariance by looking at Maxwell's equation, which then got elevated by Einstein to a full-blown theory of special relativity. So the Maxwell theory was basically the beginning of thinking about Lorentz invariance theories and special relativity. And so we know the Maxwell theory of electromagnetism is Lorentz invariant, so we don't need to do much about it. But so far, we treated matter particles non-relativistically. So in order to have fully Lorentz invariant quantum field theory consistent with a special relativity, we need to promote the matter part of the discussion to relativity as well. So that's something we have to start thinking about. So the idea is to make everything in a Lorentz invariant fashion. And so I actually need to do a quick review on how to write down Lorentz invariant theory. So as everybody here knows, the idea of special relativity is unify space and time into space-time. And so you have to treat the space and time on an equal footing. But in order to put space and time on an equal footing, then you need to make sure that they have the same dimension. Otherwise, you can't treat them on an equal footing. And that's where the speed of light c comes in. the speed of light is a conversion constant between time and space. So, you often get this question from non-physics friends that what is so special about speed of light? Why is that the speed limit of the universe? And it's just because the speed of light is just a conversion constant. We are basically using the wrong unit to measure time. So if you are born in a world where special relativity is manifest from your childhood, you probably have your watch, which has the unit of kilometer in it instead of second. It's supposed to be measured in the same unit. So the C is just a conversion constant of trying to allow us to treat time on space on an equal footing. And hence, you have this 4 vector of the coordinate in space-time, where the first coordinate, x0, is c times t, which has the dimension of length. And x1 is x, x2 is y, x3 is z. So this 4 vector is how you specify the point on space-time. And when you combine the time component and the spatial vector into a 4 vector, you say this is a contravariant vector, and you don't really need to remember this name, but the idea is that when you actually combine the spatial vector with a time component, you are supposed to put the index, Lorentz index mu, upstairs. So the superscript is the just combination of the time component and spatial vector. So that is the thing you are supposed to remember. So the mu is the Lorentz index for the 4-dimensional space-time. So mu spans from 0 for the time component and 1, 2, 3 for space. And whenever you have a 4 vector, you can find a combination that is Lorentz invariant, namely that you take the time component squared minus spatial component squared for all 3 components. And once you put together this combination, that is Lorentz invariant, so this is the proper time in space-time squared. So the idea is that whenever you have a Lorentz 4 vector, which has the index upstairs, you build an invariant by contracting this vector with what is called the metric tensor, which is a diagonal 4x4 matrix with eigenvalues +1, -1, -1. +1 is for the time component, G00, -1 is for the spatial component, G11, G22, and G33. And by summing over mu and nu indices, they are contracted by Einstein's convention, then you can see that this is the combination I just said is Lorentz invariant. And now comes the idea of using the lower index. So whenever you actually have G mu nu multiplying this vector with the upper subscript, you can define a 4 vector with a superscript, sorry. And this is the one with subscript. So the index is now downstairs instead of upstairs. And what you have to do is to multiply this eigenvalue for this metric tensor, namely to invert the signs of the spatial components. And then this kind of vector is called covariant 4 vector. But you have to be careful because the vector with the upper index and vector with lower index now has opposite signs for the spatial components of the 4 vector. But the reason we are introducing this new symbol of the lower index is that whenever you bring in 2 vectors, 4 vectors, A and B, you can define a Lorentz invariant inner product between 2 Lorentz 4 vectors. And you choose one of the index to be upper index and the other index to be lower index and sum over them. So the Einstein's convention that you are supposed to sum over repeated indices has to be done a little bit more carefully in special relativity, that you are supposed to contract indices of only between upper and lower indices. You are not supposed to contract 2 upper indices or 2 lower indices. You always contract 1 upper index and 1 lower index. And that's how you get this combination, which is Lorentz invariant. So when we go ahead and start writing a Lorentz invariant quantum field theory, we use this convention a lot. So you define all kinds of 4 vectors with upper and lower indices, and you make sure that every index is contracted between an upper index and lower index all the time, and to make sure that your Lagrangian and action for the system is Lorentz invariant. Okay, this is just a quick review. I hope you have seen it before, but if you haven't, let me know.
So are the indices, like the upper or lower just indicates which of the two possible vectors we have?
That's
and
right.
then the actual numerical value indicates which component of this vector?
That's right.
Okay.
So if you're talking about x mu with the upper index, so the x0 component is c times t, x1 component is x itself, and so on and so forth. But when you have this x with the lower index, then as the way you express the numerical values of it is given by c times t, which is the same between upper and lower index, but the spatial component x1, now downstairs, is negative x.
I see. And I guess one other thing, I guess I haven't seen this Lorentz invariant expression before. Could you just, I guess, briefly describe its relevance or significance?
Right. So this is actually the proper time. So when you have the particle moving in the space-time, then you can go to the rest frame of the particle, and how much time passes in the reference frame of that rest frame of the particle is the proper time. You might have seen expression d tau instead. Then you're supposed to put c squared on top of it to make sure that, again, you have the right dimension. But if the particle is moving, suppose you're watching this particle moving, then it not only moves in time, but also moves in space as well. And the proper time in the rest frame of that particle can be now computed in this combination of the time in your reference frame minus how much particle moved in space. And so if you go back to the reference frame of the particle, then time passes according to the ds over c, that's a proper time. But the time in your reference frame is now longer than that because you have to subtract this the distance the particle traveled in space. So your time passed more than the time in the rest frame of that particle, and that's a time dilation effect, right? So if you actually divide everything by dt, and this piece here is the velocity squared, now over c squared. So this whole thing then gives you time dilation effect of square root of 1 minus v squared over c squared. So that's the meaning of this Lorentz invariant combination. So when something is moving both in space and time, you can compute the proper time in the rest frame of that particle using this expression. And proper time is the Lorentz invariant quantity.
Oh, okay. Yeah.
Answer your question? Okay.
Yeah.
Good. Any other questions here? Okay. More reviews. So that's what we talked about as the space-time coordinates. You also have energy and momentum of the particle now put together into a 4-vector. This is the 4 momentum vector, or energy momentum 4-vector. Again, to make sure that every component has the same dimension, the time component is energy over c instead of energy itself. And spatial components are the momentum vectors. And again, you put in the momentum vector itself when the 4-vector has an upper index. When the index is a lower index, you make the you put a negative sign to the spatial components of it. And by having this p mu 4-vector, immediately I can write an invariant. So this is a sloppy notation. When I write p squared, it is meant to be the contraction of the Lorentz vectors. The same vector twice, but one with lower index, one with the upper index, to make sure that it's a Lorentz invariant combination. So the p squared, which is meant to be Lorentz invariant, is now written as time component squared, e squared minus c squared. And because there's a minus sign over here, this times that gives you negative momentum vector squared. And you all know this combination is the mass squared c squared of that particle, right? So it's the energy squared of c squared minus p squared is m squared c squared. And that's because, again, I'm sure know, the energy of the relativistic particle is given by the square root of p squared c squared plus m squared c to the 4th. And when you take a non-relativistic approximation, then m is much bigger than p. So the zeroth order term is the square root of this thing. That's the mc squared. That's the famous Einstein's equation of E equal mc squared at rest. And the first expansion in p over m gives you precisely the kinetic energy of the particle p squared 2m when it's non-relativistic. But then, of course, you have further corrections like p to the fourth over 8m cubed and dot, dot, dot. So that's the relativistic energy. And just plugging in this expression of the energy you're familiar with into this expression, you can verify that the p squared is m squared c squared. Then indeed, mass of the particle is just a number, and hence Lorentz invariant. So now you have verified that contracting indices this way indeed does give you a Lorentz invariant quantity. And especially when you apply this idea to the massless particle like a photon, then m vanishes. So you can no longer do this expansion in p of mc. Instead, the only thing you have is the square root of p squared c squared, namely the energy of photon is the c times the momentum. And also that we make sure that this relativistic notation makes sense. When you look at the plane wave solution, I put in the contraction of energy momentum 4 vector and space-time coordinate 4 vector, p dot x. Again, this dot is meant to be Lorentz invariant contraction between lower index and upper index. So that's what I did explicitly over here. You can choose p to be lower index and x to be upper index, or p to be upper index and x and lower index is the same thing. And when you write this out, you write E over C times CT, so C cancels to give you ET. Then P vector and X vector, so that's P dot X, the inner product for the spatial vector, but now with a negative sign here. And you can see that this is precisely the behavior plane wave with a du Bois relationship. So E over H bar is the angular frequency, P over H bar is the wave vector, and you get the right sign. So in a convention, we all learn in physics classes is that angular frequency part and the wave vector part has this minus sign in between. And that minus sign actually comes from this negative metric of space-time. So this is the way we obtain the correct plane wave behavior in a Lorentz invariant fashion. Okay, so this is again a review. Any questions about this? All right. And now that we talked about the Lorentz vector for both space-time and the energy momentum, we should also define the derivative for vector. So when you define the derivative with respect to space-time coordinates with the upper index, what you find is an object that has a lower index now. So just the derivative according to space-time coordinates, so the space derivatives, and a time derivative with 1 over c to again make sure that it has the right dimension, actually behaves as a vector with a lower index. And you can immediately verify this. So if you take this derivative 4 vector with a lower index, acting on x space-time 4 vector with the upper index, and the sum over indices, you find the number, which is 4. So t derivative of t is 1, x derivative of x is 1, y derivative of y is 1, z derivative of z is 1. They all add up to 4. So this lower the derivative with respect to upper index gives you something that behaves as a vector with a lower index. And once you know what is the vector for the space-time derivative, you can define a Lorentz invariant combination, again by making sure that you contract indices between upper and lower indices. So I can define 2 derivatives with the 2 lower indices, now contracted with this metric tensor G mu nu, which is the inverse of the metric tensor we had on the previous slide, but it's the same thing. It's still 1 minus 1 minus 1 minus 1. So this is the combination that is now Lorentz invariant. And this combination is called D'Alembert. And if you actually want to write this out explicitly, then the time component is this time derivative over c squared. And because the metric has -1 sign for the spatial components, I subtract the spatial derivative squared. And this piece from the spatial direction is nothing but the Laplacian. So the Lambertian is 1 over c squared time derivative squared minus Laplacian. And this is the notation you have probably seen. So Laplacian is the triangle because you have 3 coordinates, x, y, and z. The Lambertian is box with 4 corners because we're talking about 4-dimensional space-time. So the Lambertian is the generalization of Laplacian in 3-dimensional space to 4-dimensional space-time. But you have to be careful about this minus sign between time and space. So this the Lambertian is supposed to be a Lorentz invariant. So what you can test again, this idea that the Lambertian being Lorentz invariant is by using the plane wave. Excuse me. And let the derivative act on the plane wave. And when derivative acts on plane wave, then of course derivative acting on x will pull out p from the exponent. And putting h bar there cancels 1 over h bar. So this derivative will pull out p mu from the plane wave. And when you look at the combination of the Lambertian times h bar squared, you pull out this p mu twice. And of course, it's in the Lorentz invariant contraction of indices. So you get p squared. That is, of course, given by m squared c squared for a massive particle with a momentum p mu. So what I'm going to use is actually this idea that the Lambertian gives you a wave equation, which is Lorentz invariant. That turns out to be something called the Klein-Gordon equation. So that shows up on the next few slides. But anyway, so this is the review on the relativistic notation. Any questions about this so far?
Are all Lorentzian contractions like Lorentzian invariant? Lorentz invariant?
Yes. As long as you contract lower index and upper index, you get something that's Lorentz invariant. Okay. So that's a similar idea to the inner product in space, right? So if you have 2 vectors, A vector and B vector, then you take the inner product by summing over AX BX, AY BY, AZ BZ, and when you sum over them, you find the inner product, and inner product doesn't change when you rotate your system because it's given by the length A, length B, times the cosine of the relative angle in between. So no matter how you rotate the system, the length don't change, relative angle doesn't change. So the inner product is rotationally invariant. But vector itself is covariant. So AX is not invariant and rotation because AX can turn into AY. So each component of the vector is not rotationally invariant, it's covariant. But once you take the inner product between 2 vectors, that gives you a rotational invariant. So it's the same idea here. When you contract upper and lower index, which is the 4-dimensional generalization of the inner product, you find something Lorentz invariant. Before contraction of indices, you find something covariant or contravariant, depending on upper or lower index. So that's the only little complication you have beyond what you do for the linear algebra in the 3-dimensional rotation space. So apart from that little complication of the distinction between covariant and contravariant, you still have the same idea. Vector with an index is something that transforms when you change your coordinate system. But once you contract the indices, then you find something that is invariant under the coordinate change. Does that answer your question?
Yeah, I see. And just in general, Lorentz transformation is similar to Galilean transformation, but the relative speed is relativistic, right?
That's right. And that is actually what shows up in the next slide, I believe. So this is an example of Lorentz transformation, which corresponds to Lorentz boost. So the idea is that any vector gives you Lorentz invariant square. And to make sure that the Lorentz invariance of the contraction between two indices, when you do a Lorentz transformation on both vectors, let's say you're talking about A dot B, B and A both transform the same way, but they are now contracted with the matrix tensor. So the requirement that inner product of two four vectors doesn't change under the transformation corresponds to this product of matrices, not changing the metric tensor. So this is the idea that the coordinate transformation does not change the inner product of two four vectors. And just by explicitly writing out the product of these matrices, you find this combination. So you find a condition that this is a proper Lorentz transformation when gamma and beta are related in this way. And the beta has this meaning of the velocity over c between two reference frames. So when the beta is the velocity between two reference frames, and when you define this quantity called gamma, which is 1 over square root of 1 minus beta squared, and you put this gamma and beta into this matrix, that is a well-defined Lorentz transformation going from one reference frame to another reference frame, which has the relative velocity given by this velocity v. So using this idea, I can then compute what is the forward momentum of a particle, starting with the forward momentum in rest frame. And rest frame, the energy of the particle is mc squared. Time component of energy momentum forward vector is energy over c. So the time component is mc with no motion, the spatial momentum. But using the Lorentz transformation, I can go to the reference frame where this particle is moving now. And just by this multiplication of matrices, I find the answer, which is given by this 4 vector. And I can read off now what the energy of this particle is, namely that this is now the energy over c in this new reference frame. So energy is this quantity times c, gamma mc squared, which is nothing but this expression. This is gamma mc squared. And that's the expression you probably have seen before. Energy when the particle is moving is mc squared over square root of 1 minus v over c squared. Correspondingly, I can also read off the momentum in spatial direction. This is gamma mc beta. And beta, of course, here I just took this as a relative velocity, but in general, it can point to an arbitrary direction in space. So I promote this beta to now a velocity vector. Because beta is velocity over c, beta times c is velocity itself. So the c times beta becomes this velocity vector times m, and gamma, that's 1 over square root 1 minus beta squared. And that is probably, again, expression you have seen before. So the Lorentz transformation we figured out on this slide is indeed what allows you to go from one reference frame to another reference frame by relative velocity v. And this is one example how a 4 vector would transform under the Lorentz transformation so that you can really go from one reference frame to another reference frame, which is nothing but the coordinate change in 4-dimensional space-time. So this is the idea of Lorentz transformation, indeed changing the 4 vector in a contravariant way. And this contravariant vector is a 4 vector of energy and momentum. But we know that this expression still satisfies that e squared over c squared minus p squared is m squared c squared, because that combination is Lorentz invariant by contracting one upper index and one lower index. Okay, I went over time, so I stop here. Are there any questions?
I just had a very quick question. Why is the Lorentz invariance determined by the preservation of the metric tensor exactly?
Yeah, so that's the idea that we have to go back over here. This A dot B has to be Lorentz invariant. And A, if I bring this upper index, is A mu upper index, G mu nu B mu, right? So that's the combination I wrote over here. And when both A and B transforms on Lorentz transformation, there's a G sandwiched in between. And so before the transformation, I only had G mu nu in there. After transformation, I now have the matrix of Lorentz transformation G mu nu times Lorentz transformation, and they are supposed to be the same. And that's the condition I wrote over here. So Lorentz transformation of vector A, G mu nu, Lorentz transformation of vector B shouldn't change, and hence has to be the same as the original G mu nu, and that's the condition on how you can do a coordinate change from one reference frame to another.
I see. Okay. And the precise form, I mean, this isn't a completely arbitrary tensor, right? So I guess there's a particular motivation for the precise form of this transformation before we solve for beta and gamma, right?
What did you mean by arbitrary tensor?
Yeah, I mean, so we have like this particular structure of this transformation tensor, right? With beta and gamma.
Mm-hmm.
But I guess, is there a particular motivation why it is the way it is?
So the correct question to ask is that what is the general 4x4 matrix? Let me call the matrix O. Then what I have here is O metric, O transpose is the same as the original metric. That is the general condition. And this is one solution to that condition, which corresponds to Lorentz boost. Arbitrary rotation of the lower 3x3 block is also a solution to it, because an orthogonal matrix with just a unit matrix down here up from the sign is O transpose being 1. So the general solution to this requirement that 4x4 coordinate change does not change the Lorentz invariant contraction, namely this 4x4 metric, is the general condition that O, G, O transpose being G. And once you impose this condition on 4x4 matrix, then you have basically different kinds of solutions, namely Lorentz boost is one kind, spatial rotation is another kind, and general solution is always written as a product of Lorentz boost and spatial rotation.
Okay, that makes more sense. Yeah.
Okay, good. Thanks for asking the question. Any other questions? Okay, so now that we reviewed the idea of how to use this relativistic notation to write down something that's Lorentz invariant, we are going to use that idea to write down a Lorentz invariant quantum field theory using this kind of notation. So that will come up next week. Okay. Have a good weekend.
Thank you.